after this rate law overview, let's dig into the empirical rate law, which is the differential rate law for net reaction. So this is the one that comes with two names, and that on occasion leads to a little bit of confusion. So differential rate law for net reaction and empirical rate law are really the same thing. We are describing at the beaker level the rate for reaction. Reactants go to products. And this connects the rate to the current concentration. So I have a mathematical expression that tells me how is the rate, the instantaneous reaction rate of this process, reactants go to products, connected to the instantaneous concentration of the reactants. And I have the reactants only on this side. That's another source of a little bit of confusion on occasion. Why do I have the reactants only? Because I'm considering only a process that runs from reactants to products. I'm not yet going to equilibrium. Equilibrium makes the whole thing much more complicated. Not much more complicated, but it makes it more complicated. And so I'm kind of leaving the equilibrium for later. So at the moment, only reactants go to products, and then this rate depends only on how much reactants I have, on how much reactant I have. It doesn't matter how much product hangs around. So I wrote this equation out as rate, and with that I mean the instantaneous reaction rate, of course. And then I rewrote that, just to remind you, I can rewrite that as the consumption rate of my reactant here. And that would include, in this case, if I put a 2 here, and I put this 2 rather arbitrarily, it could be a 1, it could be a 3, it could be a 4. I really don't mind. I just wanted to put something so that to remind you, something can be here. And this is the whole shebang. In the parentheses is the consumption rate. This is the symbol of the consumption rate that reminds you of the mathematical expression. It's not the mathematical expression for the consumption rate, it's a symbol for the consumption rate. And then I'm going to model this with this mathematical expression. A constant times the concentration itself raised to some power of m. Okay. Sounds easy enough, right? That's not the most complicated expression in the book. So here we go. So rate, and again that's the instantaneous reaction rate, is K times A to the M. K is called, and that's just jargon now, right? But jargon is important. If you don't know the jargon, you don't know what I'm talking about. K is the rate constant, and that's a positive number. Has to be a positive number because rate is made positive, right? So K has to be positive. M is the so-called reaction order, and in this case it's really the reaction order, but it's the reaction order with respect to A. So for every reactant you get a little exponent, and so each one has a reactant, and so this is called the reaction order with respect to reactant A. And this little m is very often a whole number. More often, for the simpler the reaction, the more likely it is that m is a whole number. So if m is 1, this is called a first order reaction. If m is 2, this is called a second order reaction. And those two are probably the most frequent ones that you will encounter. 0 is possible and happens too, and we will see under what circumstances that happens. It's a 0th order reaction. 3 is pretty much unlikely, but m can be any number really. And if it's not a whole number, that indicates a complicated mechanism. That's basically what it is. If m is a whole number, that indicates something about this mechanism. Either the mechanism is simple or the mechanism is simplified. You can think in terms of a simple mechanism. If m is some strange number, that means the mechanism is complicated. So that's a good indicator. Now, just to drive this home again, why is it called an empirical rate law? So we have 2a goes to b and 3c, so I'm specifying my products here explicitly because normally I don't care about it. Just write P for products, right? And products are not specified. I don't want to write down P, Q, R for some kind of unknown product, really. So the rate, regardless of how many products I have here, is still modeled only as the reactants. And I can't say that often enough because I see all the mistakes that are typically made in other semesters. Of course, you won't make these mistakes, right? Then the K and M in an empirical rate law, and that's what I'm talking about, are obtained from experimental data. So you need measurements obtained in the lab, and then K and M are obtained from data. You can't just look at this equation and kind of guess at K and M. That just doesn't work. We shall see that there's a differential rate law at the molecular level where you can do that, right? And that's the very subtle difference between an empirical rate law at the beaker level, where you need to use data, and an empirical rate law at the molecular level, where you can look at the equation and kind of get some of these numbers from the equation. And yes, of course, that's again a source of big confusion very often. If you don't really clearly understand, are we talking about the beaker level or the molecular level, which one is true, then it can mean you're easily losing points somewhere on an exam. And you don't want that to happen, right? So in an empirical rate law, K and M are both obtained from experimental data. And in the next video, I will show you how that is done exactly.